Well, Monday, after a time change, we're all fired up, right? I don't know. Whether it's spring forward or fall back, it's always bad, okay? We're doing some nonlinear stuff, playing around with finding roots of functions. So our goal is to be able to do it for functions that have a vector variable and they're vector valued. So f takes Rn to Rn. And right now, we're working on n equals 1. So for that, we had bisection. I think you guys are playing with it in Julia right now. And then while looking at bisection, we noticed as we zoomed in on different parts of a function, it starts looking flat. So if you zoom in, and this is just sine of x, if you zoom in on different points and look at it, it gets really flat. And so you can start thinking about doing a linear approximation to the function at a point. And that's the notion of a derivative in calculus. So for those of you who have done calculus, this is a little bit of a repetition. For those of you who haven't, this will give you a good heads up. So we define the derivative at a point as the slope of the function, where slope is just like we've always done for lines. It's rise over run. The only thing is we have a choice to where we define the run, and then once we do that, we get the corresponding rise. So we can do it with a forward difference approximation where we look at x0, we go forward by a small number h, we take the we compare that to f at x0, that's the rise, and then the run is h. We can do the opposites, start at x0, go backwards by h, that's called a backwards difference approximation to the derivative. And then we can be symmetric with respect to our point x0, where we would go h back, h forward, we'd calculate the rise, and since then the run would be 2h. And don't forget the 2 when you do the symmetric difference, or your derivative will be off by a factor of 2. Okay, so this is sine of x with all the linear approximations kind of tied to it. And so the key thing here is that locally we can represent a function by a linear approximation. And there, the only thing we just need to realize is that while we're used to doing y equals mx plus b, okay, we can write a line down with any point being the key point. It doesn't have to be the origin, which is what we do when we do the y-intercept. Okay, so for here, the y-intercept would be way down here. We take a point, I called it c for a constant, then if we plug in x equals c, that's 0, so this has to equal to the value of the line at that point, and then we know that the only other thing left free in a line is the slope. And so how does this relate to a function is that this is the yc, this is the slope, and then this is the constant, x minus x0. So we get a linear approximation of a function. And then once you have a linear approximation, you would say, well, I don't know how to find this root. Hey, I'm here. Let me just follow the linear approximation and use that as my next update. And then here, I'll get another linear approximation, and then I'll follow that, and I'll get my next update. Then I get another one, and I follow my linear approximation, I get another update, and that's called Newton's algorithm. So you take your current estimate of what you think might be a root. So initially, you're going like this, or you're doing a plot. You replace the complicated nonlinear function with a constant and a slope. And then you plug in for x what your new value is, and then you solve for that such that f of x is equal to 0. And so I think at the end of class on Friday, I just went right straight to the algorithm, but here we're doing, multiply this out, keep it on one side, this, move it to the other with the minus sign, and then move this to the other sign, and it has a minus sign as well. So this is the above equation rewritten, and then as long as the slope is not 0, we can solve for xk plus 1, and this is what we get. That's called Newton's algorithm. So what I did here, I linearize, I find the root, that's my new x. I take this, I linearize again, I find my next x, and you can see here in about 3 steps, I got a really good approximation of the root. That's what all Newton does. Newton figured this out back in the 17th century. So you just put this in a loop. So I didn't have that on the lecture last time, so you just have to grab this off of here. So set x equal to some initial guess. We're going to use a symmetric difference approximation, and I forgot my 2 after I told you guys not to do that. Okay? Bad. It's so easy to forget your 2. Okay, so and then we'll go into a tolerance, let's say 10 to the minus 6. Who cares, okay? You decide what your tolerance is. There's a for loop. If you know what a while loop is, you could use a while loop. But here I just used a for loop since we've used them in Rob 101. This is xk plus 1 equals xk minus the inverse of the derivative times f of x. The only thing I'm not doing here is I'm not storing all of the intermediate values. You could just call this xk plus 1, or this is xk minus 1, and this is xk. It's up to you. You can keep track of all of them. But if it runs for 1,000 times and it's a vector with 100 components, maybe you don't need to keep all of that information. So I'm just overriding x each time. And then if my function value gets close enough to a root, I just declare x star as x, I break, and I end. Okay, so that's pseudocode, but you could program that up almost exactly like that in Julia. So it's a good place to pause and see Newton's algorithm makes sense. Question, yes?
What is n?
Total number of iterations. Okay, well, that's up to you. So this is allowing you to set a maximum number of loops, right? So n is max number of loops. And why would you want to do that is it makes sure that you stop sometimes. So you don't just start the algorithm and then it runs forever, okay? So this just gives you a maximum number of loops. So you might set n equal to 10 to the power 4, for example, 10,000. Perfectly fine, okay? Other questions? Yes, please.
So, for the for loop, is that a k equals 1 to like n? Like, is that is a k even used like in like the actual inside the loop at all?
I think the question is the index, but it doesn't show up anywhere here.
Yeah.
Yeah, so I'm just using that as a counter to say I'm going to go through this. What I've done here is just said, this is my current value of x, and then I'm getting a new x, okay? And so the next time through, this x will be showing up here and here and here. Yeah, no, it's just a way of saving memory or whatever, okay? So instead of taking all the x's and stacking them all up into this huge vector, columns or in rows, I'm just reusing x. Yep. Yeah, because it looks odd, right? Because, whoops, there's k, but there's no k. I look, there's no k. Max, you noted it too. Okay, so yeah, we're just using this to set the maximum number of times we loop because maybe we don't reach a tolerance. Or maybe this thing doesn't converge, and and you put another statement, if x gets bigger than 1,000, I know I'm not anywhere close to my root, and I bail, and I restart, okay? So you would put in the bells and whistles that you might need. Other questions on the inspiration for the algorithm? No? Let's do an example, compare it to bisection then. So an example. So this is the function that's written in the markdown box in the Julia homework, and then you're actually working with a different one, okay? So the one that's given in the Julia cell is the correct one to work with. So 0.2 x to the fifth, x to the third plus 3x plus 1, and we're going to find a root using bisection, which we've already done, and then Newton. Okay, so let me plug in the function. So there's the function. It's kind of a nasty one. And why is that? Well, notice we're dividing by the derivative. And near the root, you can see that the slope is small. So we're not going to divide by 0. Okay, so it's not like a cubic. When it goes through, it's actually has 0 slope, but it's pretty flat, and that makes it harder. If the function had been, the 0 line had been moved down to here, then that would be much easier because then your slope is very nice, okay? So, but it is what it is. That's the function, okay? So, for my symmetric differences, I'm taking h is 10 to the minus 2. For Newton, x0 equals 2 for Newton. My tolerance, 10 to the minus 4. For bisection, my bracketing points, remember that's 2 values where I know the function has opposite signs, and we use before a equals minus 2, b equals 1. And then I'm going to use symmetric differences. You could use forward, backward. There is no sideways, okay? Okay, so we're going to find the roots. I'll show you how it converges. And just as a remark again, these guys are exact when f is linear, these two. This is exact when f is quadratic. And so even the sign, it looks quadratic here very well. So the symmetric derivative is really, really good. Okay, so it does well in many different places. So the symmetric difference is a great approximation. And for those of you, once again, who know how to do derivatives analytically, you're going, I'm just going to do all my calculus and stuff. And then when you get into real life applications, maybe the function is coming from an algorithm, so you don't even have an analytical representation of the function. But then you call the algorithm, you get f at a different point, you take the difference and you calculate the derivative anyway, okay? So this is what's really cool. File, please. Quintic bisection. Come on, be nice. Don't be mean. Okay, so to get down there, I think I wrote, oh, I didn't write down how many steps. Well, although there it is, K takes 14 iterations with the bisection algorithm, okay? So this is bisection. Okay, we got our bracketing points, and then we do midpoints. Okay, maybe my laptop is unhappy with the time change. No, it's just the operator. And Newton, you can see that file is much smaller. Okay, 5 iterations with Newton, okay. So bisection is really robust. It's a great place to start learning about algorithms for finding roots of scalar valued functions that depend on a scalar value as well. So F takes R to R, but Newton converges much more quickly. You have to be ready to approximate a function with a line, and that means you need to know what a derivative is, okay? And so we never had to divide by 0, so everything was cool. Awesome? It's a great tool? Okay. Just to be very honest, absolutely no. Okay, so it can actually diverge. And if you want a fun example, I'll let you program it up. Take f of x is x minus 1 cube root. Okay, so that's a well-defined function even when it's negative, because you can take things to the cube power and get the sign. So this always has the same sign as its argument. Okay, so you could also write this as the sine of x minus 1 times the cube root absolute value of x minus 1. And this is so it's plus 1 when x minus 1 is positive, minus 1 when x minus 1 is negative. And then this would be the cubed root. There we go. Okay, so if you do that example, and you start anywhere except exactly at the root, okay, so clearly we have a root at x equals 1. Program it up, start anywhere but that, and then you will diverge. Question, yes?
First one is, are we redefining f of x as a linear equation of p stuff?
Okay, so the question was about Newton's algorithm and linearization. Yep, let me go back and do that in just a second when I finish this up. And then I see there's another remark. Does that come from, oh, from Owen, not from Monty, okay? I saw this. Okay, so the key thing though is this function is not differentiable at x equals 1. That's why Newton fails, okay? So, whoops. So there is no linear approximation to the cube root where the argument vanishes. Okay, so I'll just let you play with it. It's kind of fun. Okay, and then the question on chat, are we relinearizing at every single thing? And the answer is yes. Okay, so each time we go through the algorithm, we're recalculating a new slope and solving the corresponding linear equation. So xk plus 1, we use the previous value of x, we recalculate the slope and invert it and multiply it times f to get our correction. So yes, we are relinearizing each time we go through the algorithm, and that's what I was showing here, and we get to here, then we get another slope, and that gets us to here, and then we're almost there, we're done. Okay? And then are both of these, the question in chat is way too advanced even for me to go through it. So yes, Newton's has a little bit more computation, but in the end, you win with the extra computation in most examples. Okay, so that's how we do scalar problems. Now we'd like to move on to vectors unless there's other questions on how you do Newton for x a scalar. No? Okay, so now our goal is, because you guys are bored anytime it's dealing with x equals a scalar now. So we want to have f takes Rn to Rn, and we seek f of x star is the zero vector in Rn. Okay. Our method will be to develop linear approximations and we'll go ahead and do it when the size of the domain is different than the size of the codomain. M and N are different from each other. And then for m equal to n, we'll derive what's called the Newton-Raphson algorithm. And what that is, it's the matrix version of Newton's algorithm. I think Raphson was something like, I don't know, mid-50s or something. It's a little bit after Newton, like 250 years after Newton or something, okay? So not like they were like buddies or anything. Okay, so you see where we're going? Try to extend the idea of the linear approximation, and then we use the linear approximation to solve for an x that zeroes out the function, relinearize, get a new solution to the linear equations, relinearize, and that'll give us an effective algorithm. But what does it mean to linearize when we have a domain that is not a scalar and a range or codomain that is not a scalar? Okay. So for general m and n bigger than or equal to 1, we seek something like this. F of x is approximately equal to f at a point plus a matrix times x minus x0. Okay, so x0 is in Rm. F of x0 will be in Rn. X, x0, Rm. And hence, A is our beloved and cherished n by m matrix, okay? So we're going to replace the scalar with a matrix. Can we do that? Ooh. So the big question is, what is A? Or another way to ask it, in other words, how to compute A from f of x. Ooh. And just to set us up a little bit as a remark, when we're doing the scalar case, you might just call A because it's 1 by 1, right? It was the local slope of the function. So is there something like a local slope when we have functions that are vector valued? Some of you know the answer? I don't know. Let's play with it a little bit. Let's let the math tell us what it wants us to learn. Okay, so once again, we have f, and I'm going to just do n equals 1 to start with. Then we'll generalize that side too, okay? So we'll start out with f depending on a bunch of variables, but it's still real valued. So then f of x we're writing as f of x0. Once again, it's a times x minus x0. But now this is a 1 by m, and this is still an m by 1 because it's in Rm. Okay, just keeping track of what we have. So if A is going to look like that, it's a row vector. Let's call it A1, A2, dot, 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 AM. Okay, so that's m by 1. excuse me, 1 by m. No, keep writing it wrong. 1 by m, 1 row, m columns. Oh. Okay, so what are those coefficients equal to? Well, let's do this. Let's look at f of x minus x0 and write that as a1, a2, dot, 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 am. And then this, x minus x0. I mean, big deal. We took f of x0 over to the other side and we substituted in for a. Have we really helped ourselves out at all? Well, yeah, I'm going to make a clever choice for x. So we know about bases. So let that be the natural basis for Rm. We struggle with bases still, but the natural basis, that one we're pretty good at, okay? And just to be clear, so EI is then the ith column of the m by m identity matrix, okay? So E1 is 1, 0, 0, 0, E2, 0, 1, 0, 0, blah, 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 okay? So we can use these guys to write general x's if we want. So now I'm going to let x be equal to our generic point x0 and just perturb it in the ith direction. Okay, so I'm only changing one component of x0. Okay, well if I do that, then I've got f of x0 plus h times ei minus f of x0 is a1, a2, am. Okay. So all he did was substitute in for x. But what does this imply about x minus x0? Well, x minus x0 is just my little perturbation in the direction of the ith natural basis vector. Okay? So I'm going to make that stand out. Okay, so what does this vector have in it? It has 0 in the first component if I is bigger than 1, 0 in the second component if I is bigger than 2, 0 in the last component if I is smaller than m. So this only has a 1 in it in the ith place, and so when you multiply these, it only picks out the ith element here. Okay, so this is equal to ai times h. So I'll leave something in your notes that you can play with to figure out. If I go 1, 0, 0, I get h times a1. If I go a1, a2, dot, 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 AM times H, 0, 1, 0, dot, 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 0, 0, A2, 0, right? So that would be H times A2. Okay, so my general formula is correct. Put the H on either side you want, okay? And so now, how do I solve for AI? Well, I divide both sides by H, and I get AI is f of x0 plus h EI minus f at x0 over h. Ooh. So that's how I get the ith component of my linear approximation. Once I posed, this is what I wanted, just using my little basis vectors, I get a formula for the ith column of this row vector. Now in calculus, this has a name. It's the ith partial derivative of f, well, partial derivative of f with respect to xi, excuse me. Okay, so why xi? Let's break this down into a little bit more notation, and then we'll be basically done. So we take f makes rm into r, x0 is in rm, h greater than 0 small. And then there's this gorgeous notation from calculus. Okay, so that's called the partial derivative, I'll write that down in a second again, of f with respect to xi. So this is equal to f of x0 plus hei minus f x0 over h. But let me write this down as x01, x02, x0i plus h, x0i plus 1 dot 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 x0m. Okay, so we just put the perturbation on the ith component of x minus f x01, x02, x0m divided by h, okay? So what we're doing is we're holding everything constant except the ith component of x, and then we're getting a local slope of that. So, okay, and this is called the, once again, the partial derivative of f with respect to the ith component. the way we've written it down, this would be a forward difference approximation. And then we're free to do backwards or symmetric, it doesn't matter. I got my 2 in there. Okay, so we just perturb, whoops, xi. So it's the ith perturbation, so we're doing an ith slope. So let me do an example to help out a little bit. There's my cool example. Here it is. Okay. So it has 2 components, so we can write everything down. We'll take x0 to be 2, and then pi over 4. Come on. There we go. So here's my function. It depends on 2 variables. What have I plotted here? Okay, so here's the point of interest about which I want to calculate these partial derivatives. Here, I put x2 equal to a constant at pi over 4, and I let x1 vary. Okay, here's the point 2. What is the slope? Well, it's a line, okay? So the slope is this. There's the slope, cosine of pi over 4, which is square root of 2 over 2. Okay, here's the, on the right, I set x1 equal to 2, and I vary x2. Okay, so x2 is varying. And here's the point, pi over 4. And so this slope here, this partial derivative, it's exactly the slope of the scalar valued function where only x2 is moving. It's exactly the same as that. Okay, so you just do the slopes 1 variable at a time. I hold x2 constant and I vary x1. In this one, I already get a line, so the slope is exactly equal to cosine evaluated at pi over 4. And here, I set x1 equal to a constant, and now I've got a scalar value, so I'm calculating the derivative there. So all the formulas for the partial derivatives, they're exactly ordinary derivatives where you plug in constants for all the variables but 1, and then if you were to plot the function, you just read off the slope at that point. So that's what it physically represents. 1 variable at a time. It's the slope computed with all variables but one set to a constant. Okay, so that's what you're doing. That's what you're doing here. You're letting the ith component of x vary. All the others are locked down, okay? Only the ith component. And so you're getting the slope. You're getting the slope for the ith component. And if you change the point, you get different slopes. Does that make any geometric sense? A lot of geometric sense? A tiny bit? Negative sense? Okay, so that's what the partial derivatives are. Let's compute them really quick, and then we'll start using them on Wednesday. Okay, so let's just compute them. So the partial derivative of f with respect to x1 at x0 is equal to f at x1. Okay, my nominal value is 2, and I perturb it with h. x2, I'm putting pi over 4. This will be 2 minus h. x2 is constant over 2h. Okay, so this is x0, remember, is 2 and pi over 4. So this is 2 plus h cosine pi over 4 minus 2 minus h cosine pi over 4 all over 2h. And when you do the math, this and this factors out. The 2 and the 2 cancel. You have h here and a minus and a minus. You get 2h over 2h. Those cancel. And so you end up with, as we noticed on that first thing, you just get cosine pi over 4, which is 1 over square root of 2 or square root of 2 over 2. Okay, and then the other one's more interesting because it's messier. Okay, so I'm going to set this as 2. Then I perturb the second variable by h. If I'm doing a symmetric difference, I perturb the second variable by minus h. Then I divide by 2h. And I've got 1 minute, okay? So this is, x1 is 2 cosine pi over 4 plus h minus 2 cosine pi over 4 minus h over 2h. And so this is where you don't want to do these things by hand very much. I took h as 10 to the minus 3, and I got that this was approximately equal to minus 1.4142. And then I'll write down the true answer. Actually, it's minus square root of 2. Okay, so okay, so I've used up my allotted welcome period. let you get this. It really slopes when you freeze one variable, vary the other one. Freeze the first variable, vary the second. Freeze the second variable, vary the first variable. Those are the partial derivatives. And by hand, they're horrible. By Julia, they're a snap, okay? Okay, so we'll start using these linear approximations when we'll do the gradient, the Jacobian, and then Newton-Raphson. That'll wrap up root finding. Thank you.